Let's say you're sitting for a 5th grade geometry exam that's pretty much mostly about circles. Everybody's all prepared and all where they're supposed to, and the bell rang to declare the start of the exam. The teacher rose up from their desk and started handing over everybody's question paper, and it quickly came to be your turn. The question paper was slammed onto your desk as the teacher reminded in a sharp tone that no calculators were allowed, and they pointed towards the right side of the desk where your calculator lies. You quickly shoved it aside. No calculator? No problem. You felt pretty confident with yourself anyway. You spent the entirety of last night remembering formulas, and now they're all in your head. You know, pi r squared and whatnot. So you flip open the question paper and you got to work on the first question. But let's say you forgot the value of pi. You flip open the rest of the exam and pretty much around 90% of the question involved something to do with circles. So you conclude that you're pretty much done for. But are you going to give up? No, you won't. If some guy from 2000 or 3000 years ago could figure out the value of pi, then you thought to yourself, so can you. And so you embark on a long, treacherous path, a mathematical path, that will lead you closer to the value of pi. And so, where do you start? You think back to your previous classes, where they taught you sines and cosines and tangents. What are they anyway? Well, you put an angle in them, say x, and it gives you a value, say a for any number. And, well, we know that this value corresponds to the opposite over the hypotenuse for a triangle with the angle x. So you put in an angle and you get, as a result, whatever the length of the opposite side is, which is over here, and you divide it by the hypotenuse. Basically, you put an angle and you get some value, which is the ratio of the sides of a triangle. Okay, how is that supposed to help? Well, let's use the example of sine for now, and let's not bother with the rest. So what does this do? How can this help us? Well, what this means is that you're able to put an angle into x, let's say pi or pi half, whatever angle it might be, and that can be expressed in terms of pi radians. And what you're going to get is you're going to get a, which is a number. Now, that wouldn't actually help, actually. Yeah. So, what if, let's say, an opposite towards the sine function existed, namely the arc sine function? If we were to apply the arc sine function onto this formula, and you apply it on both sides, well, what we can assume is going to happen is that the arc sine and the sine will cancel out, and all that leaves us is just x, because you do something and you reverse it. That's what the sine and the arc sine represents. Now, what's going to happen to a if you apply arc sine? You're just going to get the arc sine of a. So now we have what appears to be something more useful. X here is an angle in terms of pi. So, all you have to do right now is, well, you just simply have to figure out a value of a, and you calculate the arc sine of it, and what you're going to get is a certain value which has pi in it, like pi half or pi fourth, and then all that's left to do is just simple multiplication, and you'd be able to get the value of pi. Okay. So what's the next step right now? So you put a value of a and you're able to get a degree in pi. Okay, why don't we make things simple? Let's say that the x value is pi. So if this is pi, what this implies for a is that it should be a value that is the hypotenuse divided by the opposite of a triangle with pi radians. A triangle which is made up of pi radian. But that is pretty hard to imagine, because pi is same as 180 degrees, which is just, well, this thing, and it would be pretty hard to imagine a triangle that's just, well, yeah, 180 degrees. It wouldn't be visually possible. So why don't we deal with smaller angles so that we can actually visualize? Let's say we're dealing with a small acute angle so that we can actually draw a triangle with that. Let's say pi over 6 now. That seems like a pretty small number, and that should make a good triangle. At least something that can actually exist so we can actually draw it. Well, pi over 6, that's same as 30 degrees. So we have a triangle that is 30 degrees, and we're just going to get the opposite over the hypotenuse, and that will be our a value. So how are we going to get the opposite over the hypotenuse? Well, that's just this function over here. So we get the sine of 30 degrees, and that will give us the opposite over the hypotenuse, which is the a value that we're going to use over here. Everything makes sense? Hopefully. So if you're a good kid and you remember the sine, cosine, and the tangent table, that thing, probably have it in your textbook somewhere, then you would know that sine of 30 degrees is actually 0.5, and that would mean that the arc sine value, the arc sine of a, the a here would be 0.5. Or alternatively, you can just simply draw a triangle with 30 degrees, and it must be a right angle triangle, and all you have to do is just measure the height and measure the hypotenuse. And if you're drawing accurately, if we presume that you're drawing accurately, what you're going to get when you divide the length of the height and the length of the hypotenuse, what you're going to get is same, 0.5. Now you have an important formula over here. So what next? Well, all you have to do right now is you're going to have to somehow calculate the value for the arc sine of 0.5, and once you are able to accomplish that, just multiply it by 6 and you're able to get the value of pi. So you're getting closer and closer, but this will prove to be one big hurdle. Now, how are you going to go about calculating the value of arc sine? How are you going to even start? Well, at best, you can't give an exact answer, but maybe approximating the value of arc sine will help somewhat. At least that will become an easier process. And what comes to mind when approximating and estimating functions is the Taylor series. Now, how the Taylor series helps is if you just keep on deriving the function over and over and over again, you can build an entirely new function out of the same function that would be more simple and useful for us. That is why it is used for approximating and estimating a lot of things. How this works is you keep deriving. You start off with the first function, which is the underived function, and you keep going down, and it's just the second derivative and the third derivative and the fourth derivative and the fifth derivative, so on and so forth. And you calculate what value that gives out when you input x as 0. Now this is going to be a really lengthy process. So if you're going to get the derivative and the derivative and the derivative all over again, you are able to build up the necessary components for building your new function. Now the f of 0, the f over here refers to the our function that we're trying to estimate, which is the arc sine. Now the arc sine of 0 is just 0, and if you want to prove that, you just have to understand that sine of 0 is 0. Pretty sure most of you know why that is. If you apply the arc sine function onto both sides, the arc sine and the sine will cancel out, and all that you're left with is arc sine of 0 is equal to 0. And that proves that f of 0 is equal to 0. That is the first term on our series. Now comes the difficult part. How are you going to derive arc sine? Well, this is an answer that you might find on your textbooks, but how are you going to hope to do this alone? Well, if you just think and write things down, well, to start with, let's just write things down. Well, our function we can call y is of the arc sine of x. Well, we can't really derive the arc sine function. So let's try to get rid of the arc sine function to make this formula something that won't. To convert this formula into something equivalent, but at the same time also not involving anything related to arc sine. Now that's simple to do. We just apply sine on both sides and that kills the arc sine. What you're left with is x simply and sine of y. And these two formulas are identical with each other because we applied the same function towards these two, and that will still give results which should be equal to one another. Now this is something that you can derive easily because you know the derivative of the sine. Now what you should do right now is implicit differentiation. So what you're going to do right now is you're going to find the derivative of this formula. Now for the right side, the derivative of x is just simply 1. And for the left side, we're going to have to use the chain rule, which is the derivative of the outside multiplied by the derivative of the inside. What you have on the outside is basically the whole thing. You derive sine, what you're going to get is cosine. And once you do that, you multiply it with the derivative of the inside, which is the derivative of y. Now y is just arc sine, but you still don't have an answer for the derivative of arc sine. So we can just simply write dy over dx, and that will be the unknown that we're trying to find in this equation. If you divide both sides by cos y, what you're going to get is that the derivative of y, or the derivative of arc sine, is actually 1 over cosine of y. But this is not the finalized product. It is the derivative of y. It is what it is right now is the derivative of y in terms of y, and that's not really useful. Well, you should convert the y to x, and that will make it more useful because we're dealing with x values all over here. Well, you can convert the sine of a y into an x. So the natural thing to do right now is you convert the cosine into sine and then the sine into an x. How can you convert a cosine into a sine? Well, if you remember one important identity, that is sine square plus cosine square is equal to 1, then that will really help. If you subtract if you subtract sine square on both sides, what you're going to get is that the cos square of y is equal to 1 minus the sine square of y. And you square root, and what you're going to get is cosine of y is equal to the square root of 1 minus sine square of y. Now, sine of y is equal to x, so sine square of y is equal to x squared. And we can write this as 1 minus x squared. So you can plug in this cosine of y, plug in this value for cosine of y, which is exactly equivalent to square root of 1 minus x squared. You can put that into here. And we're going to erase. So in the end, what we're left with is the derivative of y, where y is equal to the arc sine of x, is equal to 1 over the square root of 1 minus x squared. And this will be what we will use for the first derivative. Inputting x equals to 0, we're going to get 1 over square root of 1 minus 0, or 1 over square root of 1, or 1 over 1, and that's going to give a value of 1. The rest is pretty much smooth sailing from here on out. It'll just be really long and tedious. But let's just walk through one example. We can to calculate the second derivative, we can rewrite this as 1 minus x squared to the power of negative 1/2. And to calculate the derivative of that, you just have to follow the normal derivative rules. You put negative 1/2 onto the bottom, you get 1 minus x squared, and this one will be subtracted by 1, meaning negative 1.5. And the final step is to multiply everything with the derivative of the inside. That's just 2x. Negative 2x, I'm sorry. The negative and the negative will cancel, the 2 and the 2 will cancel, and you're just left with x 1 minus x squared of negative 1.5. Now if x equals to 0, then this will be 0, and immediately you can tell that the whole thing will end up as 0 because it's 0 multiplied by something. It's going to end up as 0. Well, you can continue on from here. All you have to do is just follow the usual rules for derivatives. It'll be long, it will be difficult, but you're gonna make it somehow. It just takes time. I won't do the rest because that's gonna take a lot of time, but I know you can do it. All you need to do is just remember the basic rules for differentiation and you'll be fine. It just takes a lot of time. Meanwhile, I have the values already pre-prepared, and that's what I'm going to write down right now. We have 0, 1, 0, 1, 0, and 9. And this will be used and these values will be used for the construction of our Taylor series. You should notice that all the even terms, or all the even derivatives we start with, this is technically considered as the 0th derivative, if you may. So all the even derivatives are going to be cancelled out because they just translate into 0. So f0 cancels, f2 cancels, and f4 cancels. So if you were to make a Taylor series for that, the structure of a Taylor series is basically the f of n of 0 multiplied by x of n over n factorial. And this is repeated as the n increases slowly for each term. Now going up till the 5th derivative should provide a good enough estimate. So let's start. We know that all the even derivatives will just end up as 0, so we're just going to apply the transformation apply the rules of the Taylor series for the derivatives that actually has a value. We're going to start with the first derivative then. Well, we have f of the derivative of 0, we calculated that is equal to 1, and we multiply that by x of 1. That's just 1 multiplied by x over 1 factorial, and we skip the second one because that will just result in a 0 for the next term. We go to the third term, we have f triple derivative of 0, that's 1, and that will be x to the third power following the degrees of the derivative. And similarly at the bottom we have 3 factorial. And next we have the fifth derivative, which we calculated, or not that, which we get to be 9. And the x value over there will be same as the derivative, which is 5. Similarly, the bottom will be the same as the derivative, which will also be 5. And there we have it. This is the Taylor series approximation for our value of arc sine. Now, our x value here is 0.5 because that's what we're trying to estimate. So simply, if we just input x equals to 0.5 equals to 0.5 equals to 0.5, and you multiply this whole thing by 6, you're going to get pi. And I'll not show that right now because I am too lazy to calculate all of this, and I do not have a calculator with me right now. But you can try this with your own calculators, and I know what you're going to get. That value will be 3.139, which we can round off to 3.14. So that is how you get the value of pi if you ever come across a situation where you forget the value of pi, but then you really need it. What this all exactly means is, basically, if you have a background in calculus, and if, let's just assume, everyone who came before you was so dumb they couldn't figure out the value of pi for themselves, then you could intuitively achieve a method to get the value of pi, and you could essentially create math out of intuition and out of thin air. And if you manage to follow along and understand that, then it means that you have the capability to essentially to invent math, as long as everyone who came before you hadn't figured it out yet. Okay, bye.